This section is about looking at polynomial functions, which is the topic of Chapter 3, and looking at definitions and language of polynomials, and also looking at their end behavior. So my goal for you is to be able to predict the behavior of polynomial functions. And to start with, let's define a polynomial function. I'm going to start in the example box. This is an example of a polynomial function. 3x squared minus 9x plus 12x to the fifth plus 6 is a polynomial function. And this is a non-example of a polynomial function. So this is something that looks a lot like a polynomial function but isn't. So if I have 3x to the negative 2 plus 5x to the 1/2. And the thing that is essential, the thing that makes the example that I wrote down an example and the one that I wrote down a non-example is that it is essential that polynomial functions have positive whole number exponents. You must have positive whole number exponents for a function to be a polynomial. Functions consist of terms, so it's essential that you have at least one term in your polynomial. A term is a part that's separated by a positive and a negative sign, or by a plus sign or a minus sign. So each of those are terms. Terms consist of a coefficient, which is the number part, and a variable part. The variable part would have an exponent on it that is a positive whole number. The variable part might be missing, like in this 6 here, and that just means that your variable has an exponent of 0, so you don't see the variable. Polynomial functions always have the same domain. The domain of a polynomial function is from negative infinity to infinity. They don't always have the same range. Eventually, you're going to learn about constant terms. Constant terms are like the 6 here at the end. Not every polynomial has a constant term, but it can have a constant term. It just means that you don't have a variable part in that particular term. It is also possible that your polynomial is given to you in standard form. Standard form is very nice, but standard form is not essential. If your polynomial is not in standard form, you can rearrange it so that it is. When we graph polynomial functions, they look like kind of wavy lines. So you might see some bumps and hills in there. They're going to be smooth. They're going to not have jagged edges. And so a non-example of a polynomial would be something that has up and down behavior but has jagged edges. That's not a polynomial. Right. Some language terms are separated by positive and negative signs, by plus and minuses. And degree is the largest exponent in your polynomial. So the degree for the first example here is going to be 2 because the largest exponent for this example is 2. The first example has 1, 2, 3 terms and a degree of 2. I recommend that you pause the video here and see if you can at least mentally answer those questions for 2 and 3. All right. So 2 has 1, 2, 3, 4, 5 terms, and the degree is 4 because that's the largest exponent. Number 3 has 1, 2, 3, 4 terms, and the degree is 3 because the largest exponent is a 3. Standard form for a polynomial means that the terms are written in order from largest exponent to smallest exponent. So this is an example of a polynomial that is not in standard form, but what we do to put it in standard form is we rearranged our exponents, our terms, moving the sign with the term. So that positive 2x cubed would be written first. It's not traditional to write the plus sign next to that because it's implied that it's positive. So if it's in the front, we don't put a plus sign with it. Negative 4x has the next largest exponent because it has an exponent of 1. And the 9 is the constant term. So the constant term would go at the end always. If you have a constant term, a term without a variable part, that it really has an exponent of 0 because it has no variable part. That goes at the end. The leading coefficient is the number part of the highest degree term. So the highest degree we have is an exponent of 3. And so the leading coefficient for this example would be 2, the number in front of that. If your polynomial is written in standard form, the leading coefficient is the first thing you see. If it's not written in standard form, you might have to do a little hunting to find it. Right? So here are some examples. I want you to pause the video here and rejoin us after you have written each of these polynomials in standard form and found the leading coefficient, the degree, and the number of terms. Answers to these problems, they're written in standard form. The leading coefficient, the first thing you see when you've written it in standard form. So it's the number in front of the largest exponent, which would be negative 3. The degree is 4 because that is the largest exponent, and this particular polynomial has 4 terms. Notice that the constant term is written last when you're in standard form. And I didn't mention, but I should mention that if you have any like terms when you're writing your polynomial in standard form, you should add those or combine them, add or subtract them together so that they are just a single term. Not in standard form unless you've combined like terms. The other idea we're going to look at is we're going to look at odd degree polynomials and even degree polynomials. So we're going to look at what they have in common and what they have that's different. I'm just putting these up here for you to think about a little bit. So here's some odd degree polynomials and some even degree polynomials. And here, these are all odd degree polynomials, but you might notice something different about them. And these are all even degree polynomials, but you might notice some patterns as you look at these graphs. If you were in class, I would have had you think about those things together. The end behavior of a polynomial depends on 2 things. And by end behavior, I mean where are the arrows pointing? So the 2 things that matter are whether your degree is even or odd, and whether your leading coefficient is positive or negative. So if you have an odd degree, even degree, then it's a lot like the x squared function, which you know really well. Both ends of that graph point upward. So that one is going to look like a U shape. If it's a 4th degree, it still kind of looks like a U shape. Not the same even U that we have for a quadratic, but similar. And both ends point up towards positive infinity. If you have an odd degree, then it's actually a lot like the line y equals x. The right side of the graph is going to point up, but the left side points down. For even degree polynomials, these things match. They both point to the same kind of infinity. For an odd degree, there's a mismatch. And the other thing I want to point out is that this line, if you have a positive leading coefficient, this line will be true. As your x's get bigger, your y's get bigger. That is a positive leading coefficient. If you have a negative leading coefficient, then your end behavior is flip-flopped. So as your x's get bigger, your y's get smaller. And as your x's get smaller, your y's get bigger. And that's also that would be a flip-flop for the even degree as well. That's a little bit like thinking about negative x squared. There's a reflection across the x-axis. So both ends point down towards negative infinity. Again, these are even degrees. Those are going to match. Odd degrees will have a mismatch. So this is another way of thinking about it. I don't know what's going on in between. Like there could be all kinds of wiggles and jiggles. But I know that if I have a leading coefficient that's odd, my right side is going to point up. And my left and right side are not going to match. But if the degree is odd, I said that wrong. The degree is odd, my two ends are going to point in opposite directions. So these ones are pointing in opposite directions because they have an odd degree. And if my leading coefficient is positive, my right side is going to point up. So for the two that I have a leading coefficient that's positive, the right side points up. And if I have even degree, then both ends point the same way. All right. So I'm going to give you a minute to try these. I want you to know that you're going to be answering this question, the limit. Oh, sorry, not limit. That's a different language. You're going to answer the question, as x goes to infinity, what happens to y? And as x goes to negative infinity, what happens to y? So you're answering those two questions for both of these graphs. And you should pause here and try to answer those questions before you watch the video. Okay, so this one is even because it's a sixth degree, and the leading coefficient is positive, so both of these are going to point up. Both of these y's are going to positive infinity. This one is odd, because the 3 is odd. So these are going to mismatch, and then because we are negative leading coefficient, our y-coordinate to the right will point down, and then they mismatch because it's odd. All right, that is the lesson for the first section of the chapter.